Well, good afternoon and welcome everyone to today's Southern Fire Exchange webinar. My name is David Godwin and I am the director of the Southern Fire Exchange with the University of Florida. Today I'm excited to introduce our guest speakers, Dr. Todd Hawbaker with the USGS and Dr. Casey Teske with Tall Timbers Research Station. Over the next hour and a half, they'll be talking about their projects developing and demonstrating a new satellite-based tool for mapping wildland fires. And now it's my pleasure to introduce our speakers today. First, today we'll hear a presentation from Dr. Todd Hawbaker. Dr. Hawbaker received his BS degree in animal ecology in 1998 from Iowa State University. After receiving his BS, he spent a couple of years burning and restoring tallgrass prairie in southwestern Minnesota, and then pursued graduate school. He received his MS degree in forestry in 2003 and Ph.D. in forestry in 2009 from the University of Wisconsin-Madison. He joined the US Geological Survey as a research ecologist in 2008 and currently works at the Geosciences and Environmental Change Science Center in Denver, Colorado. His current research with the USGS combines remote sensing with statistical and process-based ecosystem simulation models to understand patterns of ecosystem disturbances and the drivers behind them, and the impacts of disturbances on human and natural systems. Next up, we'll have a presentation by Dr. Casey Teske. Dr. Teske has worked in many aspects of wildland fire since 1993, joining Tall Timbers most recently after serving as the fire ecologist for Grand Canyon National Park. She is heavily involved in research and application development for wild and prescribed fires using GIS and remote sensing tools, gaining firsthand experience with fire during her many summers as a firefighter to help pay for school. During the summer months, she is often found on wildland fires, whether it is embedded with fire folks on the ground or providing decision support for incident management teams as a UAS pilot or as a long-term analyst LTAN. She enjoys assisting with writing burn plans and implementing prescribed burns, coordinating research and operational activities on fires, and putting her technical skills to work for fire managers doing fire research with new technologies. Additionally, she remains very involved in helping to connect students and recent graduates with internships and employment opportunities specifically related to prescribed and wildland fire, and mentoring women pursuing fire careers. She completed her Ph.D. in forestry at the University of Montana in 2012 and is very excited to be in the southeastern US and working at Tall Timbers. So, welcome Todd and Casey. I'm excited to have both of you with us today, and I'm looking forward to your presentations, and we have a good audience on the line today, so let's go ahead and get things rolling.
Great. Thanks for the introduction, David, and thank you all for dialing in. It's really impressive to see not only the number of participants in the participant window, but also just where you all are from around the world. I'm really impressed, so thank you for taking the time to listen to us today. Right, so let's get started. Our team's been working on producing burned area products from the Landsat archive, and originally we called them the burned area essential climate variable products, but more recently we're referring to them as the Landsat burned area products. In this talk, I'm going to explain our motivation behind this effort, our current approach and the products that we produce, and CONUS-wide validation metrics and results. And then Casey will follow with some examples of how she and Joe Noble at Tall Timbers have been using the data to map fire extent in Florida to better understand patterns of burning. And before I begin, I should also say, it's really exciting for us to be able to process the Landsat archive and produce these burned area products. But it's almost more exciting to see people like Casey and Joe actually use the data to do something useful with them. And I'd also like to acknowledge all the people on our burned area team here at Denver and at USGS Aeros that have helped produce the products over time. All right, so accurate and complete fire data are critical for a number of applications, including quantifying patterns and trends of fire occurrence or identifying areas of land change, as well as characterizing the drivers of fire occurrence and using that understanding to predict change, for instance, under future climate conditions or different management scenarios, and addressing the impacts, both positive and negative, of fires on a range of human and natural systems. And there's a number of existing great fire data sets available for these type of applications. Here's just a few examples. The upper left one is Karen Short's fire program analysis point location data set showing large fires, and then the upper right showing small fires and above. To the monitoring trends and burn severity point locations, they only map large fires, to the MODIS active fire detections. And because there's different methods that go into producing all these data sets, and some of them may not have consistent reporting effort over space and time, they all tell a different story, and that can leave us with some uncertainty about their completeness or conclusions we might derive from analyses with those data. So we felt there was an argument or a strong need to augment this existing fire data with additional burned area data that we've tried to collect as consistently as possible over space and time. Remote sensing is the mechanism that we use to do this. At USGS, we've got a long history in remote sensing. We've been responsible for the operational management of the Landsat satellites and the data they collect, as well as delivering it through our AROS data center. We also have a long tradition in providing data derived from Landsat imagery, such as the National Land Cover Database or the land fire, fuel, and vegetation data layers that you might be familiar with. So following in that tradition, our team here in Denver was tasked with producing a burned area product from the Landsat archive a few years ago. And when we started this work, we recognized that there was a great amount of research being done to remotely sense disturbances in forest ecosystems. But we wanted to make sure that we were able to find fires in both forest and non-forest ecosystems so we could consistently apply our approach across at least the conterminous US to better quantify and characterize long-term patterns of burned area. And because we based our approach on Landsat data, our hope is that the results will have both the spatial and temporal resolutions that are needed for large-scale assessments as well as on-the-ground management applications. So in 2017, we published our algorithm and description of the products and remote sensing of environment. We also delivered CONUS-wide annual mosaics of our results. This map shows everything that we mapped in version 1 of the burned area essential climate variable between 1984 and 2015. So we mapped almost 1 million square kilometers of burned area over 32 years. That's about 0.4% of the conterminous US burning per year and makes fires one of the largest types of land change in the country. Hopefully you can see some fires or at least patterns of burning that you recognize in this map. And we were excited because we found many of the large fires that we read and hear about in the literature and news, but we also found new fires and we mapped many small fires across the country. We went down to 10 acres in size with the version 1 products. And for us, for me coming from the Midwest originally, this was exciting because in the Great Plains and places like the Southeast, we know fire plays an important role, ecological role in many of our ecosystems, but there are very few national scale data sets that consistently characterize patterns of burning in those systems over time. We also released the burned area essential climate variable products through USGS's science-based catalog and our center's FTP site. If you Google USGS burned area essential climate variable, science-based should show up as one of the top hits and you can find them there. Since then though, we've refined our approach to incorporate Landsat 8 data and utilize the new analysis-ready data format that the Landsat data are being delivered in. We're calling this version 2 Landsat burned area products. These new products are being routinely produced by the USGS's AROS data center and being delivered through the Earth Explorer website. This is the same website that you'd go to download the raw Landsat data. If you go here and click on the datasets tab, expand Landsat, and then expand Landsat Collection 1 Level 3, you'll see the burned area product there next to the other 2 products we're producing, snow-covered area and surface water extent. And also if you Google Landsat burned area, you should find this website as one of the top hits that describes the products and the algorithm behind them. So in the rest of the talk, I'm going to try to focus mainly on the most recent version of the algorithm and the products it's producing and our CONUS-wide validation metrics and results. And a little bit about the differences between the two. So the first one, the burned area essential climate variable, version 1, was based off of the World Reference System path row data. This was the sort of native data format that Landsat data were delivered in. And the paths kind of, come north to south across the country here, and there's some overlap between them. And if you're interested in doing a time series analysis, these overlap areas between the paths are really important, because with any given satellite, you get an 8-day revisit interval there. In the non-overlapping areas, you get a 16-day revisit interval there. And a lot of us at USGS and at other agencies and institutions were kind of frustrated that we'd have to download different path rows and pre-process them to a common spatial extent. So USGS listened, and now they're delivering data in this tiled scheme called the analysis ready data tiles. Each one of these squares is 5,000 by 5,000 pixels across, and all the original path row images are cropped down to fit within that 5,000 by 5,000 pixel frame. So here's an example for ARD tile is outlined in red. This is horizontal coordinate 28, vertical coordinate 11, covering part of North Carolina. And you can see the 4 corresponding path rows that overlap it. So as we move through time through the image archive, you get one image from path 15 here, and the next one from path 14 there. And the images kind of jump around. There's some no data there. But the nice thing is this really facilitates processing for us and simplifying our coding on our end, because all the data have the same row column count, same spatial extent, and it maximizes the overlap it minimizes the revisit interval in these overlapping areas right here, and that really facilitates time series analysis. So all of our products are now based off of the ARD tiles. All right, here's how our algorithm works. We designed it to consistently characterize burned area across all ecosystems using every usable Landsat 4, 5, 7, or 8 image, anything with up to 80% cloud cover. So for each Landsat image or scene, we produce a burn probability image using a type of model called a gradient boosted regression model. This is a machine learning technique, and it's kind of like classification and regression trees on steroids. If you're really interested in them, I'd be happy to talk to you for hours about them offline, but I won't go into too much detail here. They do require training data, though, and to generate our training data set, we placed points in known fire locations using the MTBS large fire footprints to do that, and then an additional suite of unburned points across our training sites. And then we drill down through all the images in our training ARD tiles and grab values from the different Landsat bands. From those, we derive our predictors. The only predictors we use are derived from the Landsat data, so we don't incorporate any existing land cover or topography or any other data like that. The predictors we use at the scene level are Landsat-derived spectral indices. We also produce 3-year lagged means and standard deviations for each spectral index, and then a change between the scene level spectral index and its 3-year lagged mean. Once we fit our gradient boosted regression model, we can then use it to generate wall-to-wall burn probability surfaces like this example shown here. This indicates that a probability that a pixel did burn. Red areas had higher probabilities, green areas had lower probabilities. And a lot of people just like these data as they are. They can do their own thresholding to make sure they're identifying the fires that are of interest to them. We do provide a scene level burn classification product that we generate from our burn probability surface using a pixel thresholding and sort of object-based segmentation approach. In this case, the classified burned areas from this example are outlined in black. So you can see they capture the exterior fire perimeter, but they also capture interior unburned patches as well. And for some applications, those might be important to consider. In addition to generating the scene level products, we also do annual composites that I'll talk about in a bit. In version 1, we used a fairly limited suite of spectral indices. In version 2, we combed the literature and came up with a larger set based on studies that were using satellite imagery to map burned areas or severity around the world. Here's the list. I'm pretty certain there's still other ones that we could add. But we tried to be inclusive, and gradient boosted regression models work really well with large volumes of data. And even if your predictors are correlated, they don't really seem to affect them very much. The challenge with using this many spectral indices comes more at a computational cost. And so to make our algorithm efficient, we implemented a variable selection procedure where we tested every possible predictor, added the the predictor that increased accuracy the most to the model, and then tested the remaining ones. And so here's the suite of predictors in our model. We start out with this NBRT1 metric. It starts out with a AUC, or area under the curve of a receiver operator characteristic plot. And you can see that AUC value kind of increases as we add predictors and levels off just under 99%. We only selected 8 predictors in our model, in our final model, and then their relative importance is shown by these gray bars here. And so these are either capturing spectral changes induced by fires that cause decreases in biomass or increases in ash and charcoal or bare ground cover, or in the cases of the lagged means, they're capturing sort of pre-fire conditions that separate places that can burn from places that can't burn. All right, so here's some examples of the time series of our result. This is for that same tile in North Carolina. The date is going to be shown right there. Let me switch back. This first image isn't too exciting. This is the raw Landsat image with a few clouds in it, our burn probability in the middle, and our final burn classification on the right side. If you look closely, you might see some red speckling in there, but there's not a whole lot going on till this next image, which shows the Allen Road fire that burned here in the Poquoson Lakes National Wildlife Refuge in 1985. You can see we picked it up with these reddish areas in our burn probability image. Part of it was also masked as water. This is an artifact in the Landsat quality assurance bands. The algorithm that generates those often confuses burned area with water. So sometimes you get results like this. And here's our final burn classification. No worries about those water areas, though. They start to disappear as we move forward in time and collect more images. And so one nice thing about looking at every image in the Landsat time series is that we can keep track of how many times we've mapped a pixel as being burned over time, and that allows us another confidence measure of what has burned and what hasn't burned. And then finally, I threw this image in there because it kind of shows that even when we have high cloud cover, we can still pick out the burned areas in between the clouds. And this is really important in places like the Southeast, where there's often a fair amount of clouds in our images. Oops. All right, so we have these scene level burned area products for each image in our time series stack. And then we also generate the annual composites. And those consist right now of the maximum burn probability for each pixel across an entire year, the burn classification count, which everything here is mapped in red, but it actually maps the count of how many times a pixel was burned. And then the Julian date of the first Landsat image we observed the burned area in. So we designed these to help end users, to give end users a little bit more information to identify fires that they were interested in. So you might be wondering how good the results are, and you probably saw some things that looked a little bit wonky in some of these images, maybe some places that we mapped as burned that might be something else. So this is where the validation side of things comes into play. For any remotely sensing effort, especially ones that cover large spatial and temporal extents, validation is a really critical piece of product creation, as it provides our end users with quantitative accuracy estimates to help them determine whether or not the products are any good. And for us, it also gives us a benchmark to improve our products as we're moving forward. The usual approach taken to validate global coarse resolution products is to compare them from data derived from an alternative source of images with higher resolution. For instance, comparing MODIS data to Landsat data. And that kind of model works well for Landsat data from more recent years, where we can use commercial high resolution satellite imagery to validate our data. But it's not a viable option over the entire length of the Landsat archive. When you get back into the 80s, it's hard to find very much commercial high resolution data at all. And it's even more difficult to find something that has a burned area in it. So the farther we go back in time, the only viable option is to really validate Landsat products with Landsat data. Thanks to Melanie Vanderhoof's effort at our center, we validated the burned area essential climate variable version 1 results using both approaches, both with Landsat and high resolution commercial satellite imagery. She had 2 really nice papers where she published her findings that came out in 2017. And we're using those same data sets to validate the version 2 data as we move forward. Just to kind of try to keep things on schedule, I'm going to focus on validation of our products with reference data that we derived from Landsat imagery. Before I do that, though, I wanted to explain where the bar is at. And we looked at the existing global fire products that are out there that are being routinely used for global, national, and regional scale analyses. Especially Mark Padilla's 2015 paper is kind of the reference that we're using, although I think there might be some newer work out there now. Omission errors, where we have false negatives, and commission errors, false positives, are surprisingly high for some of these products. Omission ranges between 68% and 93%, and commission ranges between 42 and 94% respectively. For the global products, the best game in town right now seems to be the Modus MCD 6.4 burned area products. But this is kind of where the bar is at, and we're hoping that we would be somewhere within that range. When we produced version 1 of the burned area essential climate variable, we were pleasantly surprised that we had lower error rates than the global products. And it might be somewhat expected since we're only working at CONUS, we're not covering the entire globe, so we might not have many of the same challenges as these global products. But in the end, our omission rate was about 42% and our commission rate was about 33%. We found that our errors were lower in more natural ecosystems and our errors decreased as fire size increased. And so our hope in producing version 2 is that we would sort of do at least as well as the version 1 with our error rates. Producing the data, we do a lot of visual assessment of our results. And here's an example for using our high resolution validation data for the Sweet Farm Road and Big Turnaround Complex fires that burned part of Okefenokee National Wildlife Refuge back in 2007. So in the top middle, there's the raw QuickBird image. In the top right, we have the burned areas that we derived from that QuickBird image. Red areas are burned. On the bottom left, we have the Landsat image that has the most or the closest date to the QuickBird imagery. You can see the burned area in that quite nicely. The black outlines show the MTBS perimeters for these fires, by the way. And then bottom middle, we have our version 1 product, and bottom right, we have the version 2 product. So looking between version 1 and version 2, we were quite pleased that both products seem to map burned areas within the perimeters fairly well. We were also quite pleased with version 2 in that it seemed to get rid of a lot of the noise outside of the perimeters. So to us, this looked like an improvement. When we compared the version 2 results to our QuickBird reference data for this extent, the omission error was about 4% and commission error was about 33%. And hopefully you can see the differences in the commission error are largely because of differences within the fire perimeter. Some of that's due to date mismatches between the QuickBird and Landsat data, and some of it's just due to differences in imagery, and some of it's just due to errors in the classifications. Here's another Western example. This shows 3 fires that were mapped by MTBS in California in 1998. Here's the Landsat image for October 21st, and then the reference data that we derived from it. You can see there's quite a bit of patchiness within the fires. And then version 1 and version 2, both versions found those fires. They tend to be a little bit patchier within the perimeters than our reference data did. And comparing version 2 to the reference data, we had about 25% omission error and just under 30% commission error. And between the versions, we see that we're picking up a few more burned areas in these agricultural areas kind of on the east side of the scene. So when we quantified the results for both version 1 and version 2, here's what we have. Version 1 had 42% omission error. The numbers in parentheses are the standard errors, 33% commission error, and slightly underestimated total burned area by about 14%. In version 2, our omission and commission were balanced right around at 40%. We were pleased that our omission error was similar, kind of in the same ballpark with version 1, but we got pretty nervous when we saw this 11% increase in commission error, and it kind of left us scratching our head wondering what was going on. Our initial thought was to go back to images like this and see where we were picking up more fires in agricultural areas. So we decided to split out our validation metrics by land cover types, specifically looking at commission error. And as you can see in this graph, in both versions, in pasture, hay, and cultivated crops cover types, our commission errors were quite large, above 60 and 70% in all cases. So that wasn't too surprising for us because identifying burned areas in agricultural land cover classes is challenging with Landsat given its relatively long revisit interval, and it can make that long time interval between images can make it difficult to separate burned areas from other types of disturbance like tillage. So we asked then, well, how do our metrics change if we toss out those cover classes? And lo and behold, they got better for both version 1 and version 2. We focus on version 2, where our omission error dropped by 4% down to 40%, and our commission error dropped from 44% down to 27%. So that made me rest a little bit more easily at night. Another issue that end users identified in the version 1 products was that we were repeatedly mapping burned areas across years. And this is an example showing the Pagami Creek fire that burned in northern Minnesota in November of 2011, up in the Boundary Waters, if any of you guys are familiar with that area. And in our burn probability and burn classification images, we mapped it in both years, and actually probably did a better job mapping it in 2012 than we did in 2011. The problem is if we just release products like this, and we're using our data to look at annual patterns of burned area, we end up double counting it. So what we've done is we've implemented an extra filtering step that determines if any burned area in the annual composites overlaps with large burned areas in the previous year. And if so, it takes it out of 2012 and assigns it to 2011. This is our filtered burn classification product, kind of showing the best of 2011 and 2012 there. And then that fire is completely gone in 2012. So we don't have that double counting issue anymore. And when we do this, it decreases our commission error a little bit down to 25%, but also comes at the expense of increasing our omission error by 1%. Finally, to put this back into perspective with everything else, we were quite happy because we had a slight increase in omission error accompanied by a decrease in commission error. So we thought those were reasonable trade-offs given that we're incorporating now Landsat 8 data. We've adjusted the new ARD tile format, and we've simplified and made our processing stream more efficient. When we map the new version 2 results out across the country, this is what we've got. We've mapped out the pasture, hay, and cultivated crop cover classes here with that light gray. It doesn't look too horrible when we don't have that mask on there, so don't feel like we're hiding anything. But from 1984 through 2017, we mapped a little bit over 900,000 square kilometers. That's still about 0.4% of CONUS per year. But, and there's still some issues you can probably see, like we've got some streaks here in parts of the West that we've got a technician going in and figuring out which scenes those occurred in, so we can filter those out before we release the final products. But in the end, I think this is really cool because we're mapping burned areas at 30-meter resolution over 34 years. And so I think this is a nice consistent approach for monitoring patterns of burning across CONUS. We look at our annual estimates for both version 1 and version 2. They consistently map more burned area than MTBS. Usually we're following kind of the same year-to-year variability, so that makes us feel better. But we're mapping quite a bit more fires. Some of these are large fires, but a lot of it is because of fires in the Great Plains in the Southeast. On average, we map about 120% more burned area per year than MTBS. All right, so finally, our work demonstrates that consistent scene level and annual products can be derived from the Landsat archive. And for us, having arrows produce the level 2 surface reflectance products and their quality assurance layers are really critical to that. It lets us focus on mapping burned areas and not sort of the mundane side of remote sensing. Our validation efforts show quantitatively that our products have lower error rates than existing global coarse resolution burned area products, but they also show that mapping burned areas in agricultural land cover classes is challenging, and that limits the use of our results in those type of cover types. For the remaining cover types, our products are unique in that they map all fires larger than 5 acres in size and have a 35-year and growing time series. And when it comes to remotely sensed information about fires, I think our data have the finest spatial resolution and longest time series available. We do show a greater extent of burned area than existing products, but because of that, we also feel we're providing a new information source to help us understand patterns and impacts of burning, especially in places like the Great Plains and Southeast where those data can be hard to come by. And finally, we have an active and growing community of stakeholders that we hope will continue to benefit from routine production of the burned area products. And we love engaging with people who are using our data. So if you have any questions about how to use our data or how to interpret the data or how they were produced, please do feel free to contact us. My contact and Melanie's information is listed here in this slide, along with our journal articles and links to the burned area ECD version 1 and version 2 data in USGS Earth Explorer. And with that, I think we can hand things over to Casey, and I'll stick around to take questions at the end of the talks. Thanks for listening.
All right, great. Thanks, Todd. I'm switching over screens now, so we'll see what happens here. Are we on the right screen, David?
Yes, Casey, that looks good. Thanks, Todd. And Casey, your audio sounds good and your video looks good too.
Okay, great. So I just wanted to reiterate thanks to everybody for joining us. We've been really having a good time working with Todd and Melanie on our project using the burned area products that they've provided. And so I'm going to talk to you today a little bit about a case study or an example of ways that these products can be used for management programs. So I'll walk you through a project that we're working on with the Florida Fish and Wildlife Conservation and the Peninsular Florida Landscape Conservation Cooperative using the burned area products. And so I'll walk you through that project, and then at the end we'll take all the questions. So first off, this project would not be possible without the help of a bunch of people and organizations that provided data for us. And specifically, we got funding from the Fish and Wildlife and the PFLCC. And then we had a number of data calls and data dumps provided by a variety of individuals within the various organizations listed on this slide. So a big thanks to everybody for helping us out and trying to put this to work in Florida. So with that, the reason that we got funded to do this project is that we've known for over a decade that monitoring fires has been an issue in the state of Florida, both on public lands and in private lands, and especially when it comes to species management questions and needs, conservation questions. And the best way that we can highlight how important it is to understand these things in Florida is that Florida is roughly 70% private ownership. 23% of the state is in public or conservation lands where fire history data sets are actually maintained, but this large area of private ownership, we don't necessarily have fire records. So when we're trying to answer conservation questions that deal with fire and species dependence on fire, it could be an issue. So we were tasked with coming up with a way to try to address this question, and we ended up developing a spatial database modeled off the Department of Defense's wildfire database that's been in use at Eglin Air Force Base for almost 2 decades now. And we decided to start looking at fires across the state of Florida. The first step was to look at the authorization data. Florida requires all burners to get a permit if they're going to do a prescribed fire or a pile burn. So we wanted to use those authorization data and also remotely sense data to start understanding the footprint of fire across the landscape. And with that, we wanted to be able to query those areas and understand conservation and species-based questions as they related to fire in this area. And then finally to update that as we move through time. So basically you could get summary reporting, you can customize queries, you could provide spatial information in the form of maps by using this kind of a system. So that's what we were funded to do. So we kicked off our project with a workshop in about 2017. It was September 2017, I think. And we basically went through highlights of the existing DoD fire database and some of these different products that are out there that currently map fires, and asked end users and users of this kind of data what kinds of questions they'd want and how could we best populate this database just to get a starting point. So with that, we had a data call, and we had over 20 different land ownerships provide us data on their fire history on the lands that they managed. This isn't a full list, but you can see the variability of the different kinds of data that we were receiving. We had fire occurrence data, we had fire history data, we had progression data. The time spans ranged from the early 70s all the way to the present. Some of the data included wildfires, some of it was just prescribed fires, and the characteristics depending on the source were also variable. So there wasn't a standard, but we ended up with a lot of data sets that could help us address these questions of where are fires occurring in Florida and help us validate some of these Landsat-based data sets that we were thinking of using. So I'm going to give you a little bit of background on just how much fire happens in Florida so you can understand the scope of the problem. So while we're waiting for our data sets to trickle in from this data call, we started exploring the permit database, and it's called Authorizations in Florida. So if I interchange the two, that's what I'm talking about. An authorization and a permit are the same thing. So we began exploring this database, looking at data from the years 2006 to 2016. And basically any person who wants to burn a piece of land in the state of Florida, whether it's with a pile or a broadcast burn, that person is required to get an authorization. So you go online and you talk to the dispatchers and you tell them where you're burning, how big it's going to be, what date, why you're burning, how you're going to do it, all that kind of stuff. And it comes onto a public facing web page that other people can see where you're burning. So we were able to get this a data dump from the Florida Forest Service with all this information about where fires are occurring across the state of Florida. And this is specifically prescribed fire. So what you can see in this map is, for whatever day this was a couple weeks ago, there's a lot of pile burning occurring in those purple points, and the green pins show where prescribed fires are occurring. And so for any given day, the burning in an area is plotted on this map. And we're burning a lot. These are all in acreages, but you can see that without counting sugarcane, which accounts for a ton of burning in this state, we're getting nearly 100,000 authorizations per year that account for 1.5 million plus acres burned per year and 120,000 piles. So that's a lot of fire. And again, 70% of the state is private ownership. So where is this fire happening if we're not keeping records? That's kind of the question we're trying to ask. So we start mining that data as we're waiting for the data sets to come in, and you can start to see the distribution of fires. Most of our burning is occurring in the winter months, as you can see on the left-hand slide. January, February, and March is where we get a lot of prescribed fire happening. Then we slow down through the summer season and then start ramping back up in the fall. You can start to see the variability between the different years as the burning has gone on. You can start to see the distribution spatially on a yearly basis. You could start comparing between years, and you can also start to compare between months with this data set. So you can start to see a lot of different things with this data. Perhaps my favorite might be this distribution of numbers of authorizations versus how many acres were authorized. So what you can see on the top with that blue circle is that we have a lot of authorizations that are occurring between July and September, but most of the area is being burned between January and March. And then conversely, down south in that purple circle, what we see are very few authorizations in that July to September timeframe, but the area burned is pretty evenly distributed throughout the year. So these are just some of the different things that we can start to understand with this data. Another thing that proved to be very helpful for us to understand is that just because a place is burning doesn't mean that there are multiple authorizations issued for that place. So in this example, the 2 red stars are each associated with a given burn date. And you can see a red line connecting each star to a couple yellowish units that were also associated with that same burn date. So one authorization for multiple acres could represent multiple disjunct burn units. And so if we're trying to use this authorization data to help us understand spatial representation of fire, while we're getting lots of descriptive information, we're not getting exact spatial footprints, and that might not be even close to where the fires are happening. So we're getting good data. We evaluated a handful of other data sets, and here's a handful that Todd's kind of talked about: the MTBS data, the Modus Active Fire products. We even looked at some of the VIIRS daily products. And ultimately, we decided to settle on these burned area products. And I have it labeled as BAECV because I just found out in Todd's talk that they changed it to burned area. So I apologize in advance for that. But that being said, it's the same thing. So we felt that this was a great product after talking with Todd and Melanie to start identifying exactly where fires are happening in the state of Florida, considering that we're burning as much as we do every year. The data, it's replicable, it's standardized, it's available nationally, and you're not relying on some fire tracking system to trigger production of these results. And so we were able to use the version 1 products, and now we've rerun everything using the version 2 products for 2006 to 16. And we chose 3 different pilot areas across the state just to test these against. These places have lots of fire that occur on their ownership. They have a lot of ecosystems and species of concern that are needing to be managed in appropriate ways. And they represent a variety of ecosystems. So we initially used a specific threshold of 90 to 100% with those burned area annual products, the 90 to 100% burn probability, and did that across the whole state and validated against landowner records and meetings with managers in these 3 areas. And so just to clarify the differences, what you see on the top here, the top portion of the slide is the 2006 to 16 burned area as represented by burn units and the years that they were burned from the Eglin Air Force Base fire history data set. On the lower left, you can see what that same time period looks like in terms of the number of permits issued or authorizations issued for prescribed fire on Eglin Air Force Base. So you're already starting to see some differences. And then on the lower right, I know it's current up to 2018, but you start to see a little bit more of a mosaic pattern, and that's using that burned area product at that 90 to 100% probability. So I'm going to walk you through some results using this data for the Apalachicola National Forest. I'll highlight them, and I'll pick on tall timbers as well. I pick on everybody in this talk, so we all get highlighted and made fun of a little bit. So basically, we found that BAECV is a great spatial representation of burning. The black units are a burn unit for a given calendar year. The red areas are areas that BAECV detected a fire at the 90 to 100% burn probability within that same year. And in most instances, we're capturing a mosaic across the landscape of what was burned. You'll notice that there are a couple areas where there's a burn unit, a black area without any red on it. And you'll also see red areas without any black underneath of them. So the black areas without red are likely late year burn units. So in this slide, a black area without any red on it was probably burned in November or December of 2011 and would not be detected until perhaps January of 2012. So because we're using a calendar year attribution, we're misattributing some of the timing of the fires, but the area still gets attributed at some point. You'll also note those red areas that don't have a black background behind them, and that's probably a late year burn from 2010 that was actually detected early in 2011. So again, that's where the that attribution wiggle room comes in. You're getting the area burned, but it might be incorrectly attributed in terms of the year that it actually burned. That being said, we felt in talking with the managers at all these areas that we were getting a great special representation of these fires. This is Bradwell Bay Wilderness on the Apalachicola Forest south of Tallahassee. What you see are burn units, and the hatching within the burn unit is what is considered burnable area. Everything else is water, and when we look at 2011, what was detected as burned, it lines up with that burnable area. So it's doing a really good job there. We did have some issues down south in the Everglades and Big Cypress area, which is a water-dominated ecosystem. That 90 percentile burn probability was not necessarily capturing as much fire as it was in other locations when we were looking in these water dominated ecosystems. And so what you see on the left are 2011 fires with in the black representation is what we're seeing with the 90 to 100% burn probability. And you'll notice a couple fire parameters that don't have any really black mosaic of burning within them. So we decided to re-threshold based on land cover and lowering that burn probability down to 70%, and to see if we could try to increase the amount of fire in those areas that we were burning. And you can see that it did a little better job, but there's also a lot of noise in there. And so there's still some work to do. We'll have to continue some conversations with land managers and those kinds of ecosystems, but just knowing this moving forward and being able to have people on the ground paying attention to these kinds of things, I think we can really start to suss some of this stuff out. Another issue with any kind of satellite-based data in Florida is that we have a lot of cloud cover. We have rapid green up, and we have a lot of low intensity fires. And so those can be challenging things to discover in terms of detection from satellites. And so what I'm going to walk through is a couple months series of Landsat 5 data here at Tall Timbers. What you see in the black is the Tall Timbers boundary. The yellow outlines are the 2011 area burn as mapped by the version 1 BAECV. And as this is a March 20th, 2011 Landsat 5 image underneath. And so you'll notice as I move forward that some of these areas are starting to show up as burned and other areas are disappearing. This is a May 7th image that's, so it's 2 months later. And then we go through the cloudy summer season. The next good image is October 30th, and you can see that nothing looks like it actually burned. So I'll repeat that sequence real quick, but you can see the March 20th, May 7th, and then October 30th. So using this burn probability mechanism, because it's operating on a scene level, we're able to kind of summarize those areas that burned, even if we're missing it in some individual scene, and come up with a good way to look at fire. So we're able to look at fire history metrics now so that we can start to answer some of these conservation questions. So here's the Apalachicola again. This is how many times it was burned in a specific location between 2006 and 2017. We can look at how many years it's been since it last burned. So perhaps a species needs fire every 2 years. So you might want to hone in on some of these red areas because it's been 5 or more years since it burned in that same time period. We can look at specific years that the last time a fire was detected in a given area. And we can start to look at something like long fire-free intervals. So you can start to see these patterns changing and understanding the different kinds of questions you can answer with some of these kinds of metrics. And then on an individual annual level, we can start to tease out some of the seasonality. So here's a 2006 image that shows dormant and growing season as it is burned through the year. So you see spring, summer, autumn, and winter, as well as dormant and growing season. So we're able to start capturing some of the things that conservation managers are interested in asking questions about. We validated against the 3 pilot areas, and we've developed all these maps across the entire state. We've used, we're now up to using the version 2, and it's complete from 2006 to 2018 for the entire state. And some of the species conservation questions that we are really excited to start drilling down into or something like this. Perhaps you're interested in gopher tortoise habitat and you want to see how many times an area that is gopher tortoise habitat has burned. So what I'm showing here on the big slide on the right is the number of times that gopher tortoise habitat has burned within the Apalachicola National Forest between 2006 and 16. So that's the old-fashioned way of doing it. With our new database, we're putting things into things like Portal. So you can start to query, show me where within this blue square we can see gopher tortoise habitat that might have it's been longer than 3 years since it last burned. So we can start to query specific areas, and when that returns your query in a spatial manner, you can you can see those locations where gopher tortoise habitat is and time since previous fire has been more than 3 years. And so this can help highlight successes, and it can also identify areas that might need some work. So what's next? Well, increasing opportunities for detection, maybe with Sentinel satellites or other sensors that might come through in the future. We're looking at improving some of those detection algorithms with the USGS in places like the Southeast, where some of the areas are a little harder to identify. We want to keep on advancing the database. We want to work it back through the entire series of the Landsat data through 1984. Right now we're 2006 to 2018, so we want to go back in time a little bit and then understand some of the other user needs. So with that, I'll leave it up there, and I will also throw on the journal articles that Todd had on there. So that's all I have.
Alrighty, well, thank you, Casey. Once again, if you joined us during the presentation today, my name is David Godwin, and I'm the director of the Southern Fire Exchange Program. And we just had presentations from Dr. Todd Hawbaker from the US Geological Survey in the Denver area, and Dr. Casey Teske from Tall Timbers Research Station in Tallahassee. At this point, we have time remaining in our event today to address questions from the audience. So we do ask that you please type your questions into the Q&A window in Zoom, or if you can't get that to work, you can go ahead and put them into the chat window. So we already have some questions that have come in, and we're going to go ahead and try and get through those. If you're still working on your questions, you can type them in. So we had one that just came into the chat window from Rob. And is the BA2 version available now, or is it soon to be released?
Yeah, I'd be happy to answer that question. Rob, the BA version 2 data, the sea level products are available through USGS's Earth Explorer website. We had a slide in there that kind of showed you how to navigate that, but they are in there. We are still working on finalizing the annual composites, and it remains to be seen whether or not those will be delivered through Earth Explorer or through our center's FTP site.
So while we're on the Earth Explorer, question came in from Kim, and she's asking how often are the new data available on Earth Explorer? What's the frequency there?
That's a great question. Right now, I believe we have everything processed through the end of 2018. And I believe Gail Schmidt is the contractor at Aros who's kind of taken the lead on the routine processing. I'm not sure that she's been able to start the 2019 data yet. For better or worse, we have not had many large fires show up in 2019 yet that we know of. But I think they're still working out some of the kinks about which computing system they're actually going to process the data on. But the hope is once it is fully operational, that there'll probably be about a 2-week lag between when the Landsat imagery are collected, when they can get the surface reflectance products generated, and then when they can process the burned area products.
We had a question come in along the same lines of the Earth Explorer. Are there tutorials or tools or instructions to help find that data in Earth Explorer to help people walk through that?
No, there are none that I know of, other than any tools that might already exist for Earth Explorer. But if that's something that people really could find useful, we could see about producing maybe a quick video and putting it up on our website or on YouTube or something like that.
Okay, we've had a couple people ask about that, so it might be something.
Okay, great. That's good to know.
Looking into, yeah. So we had a question that came in asking with experience regarding mapping marsh habitat and coverage in Louisiana. And I'm going to expand on that and add a question about mapping wetlands. In Casey's presentation, she said that the areas in South Florida and the Big Cypress and the Everglades, there were some issues with detecting fires down there being wetland ecosystems. do you have a sense of how well it's able to detect the presence of fire in wetlands that might be embedded in uplands? Because I know there's a lot of interest and issues related to wetland habitats in the Southeast and how much fire they're getting.
Yeah, sure.
Oh,
Sorry,
go ahead,
Casey,
Todd.
go ahead. No, you please.
Okay, I was just going to say, just knowing with that version 2 stuff, we really saw an increase in the ability to detect fires. So I haven't had a chance to, we just finished processing that like last week. So we're currently updating that database, but I haven't had a chance to go down and reassess down in the Everglades area with that. But what we were seeing from stuff locally where we do have, you know, ponds that dry up and ponds, wetlands in the uplands and stuff like that, we are actually getting better detection rates in those areas. So I think that's promising. And we're going to be going down to St. Mark's National Wildlife Refuge and doing some work down there. So we'll be able to kind of get a better handle on some of that now that this version 2 is out. And but we are seeing, we have some ideas on how to process that, and we are seeing better detection now with this version 2.
Great. Well, that's encouraging. We, as you guys move forward with that, we may ask you to, at least Casey, to come back and talk about how well that works for detecting fires in wetlands, because I think there'd be a lot of interest in that across the region. Quite a few other questions have come in. One, a quick one, will there be a PDF of the presentation? Are you guys able to share either of your presentations in the future as we get the archive posted?
Yes.
Yes.
All right, great. Well, thank you for that. We appreciate that, and we'll work together to get that up there. We had one that came in from Brian. This is for Todd, and he says, does your filtering step in terms of trying to deal with issues of double counted burns that you provided the example from the boundary waters, does it distinguish between true double counting and cases where the area had prescribed burns in consecutive years? Oh, that's interesting.
Yeah, that's a really good question. It should, because I forgot to mention in the talk that we've only implemented that filtering step kind of in the upper Great Lakes states, excuse me, and in the Western US. I don't believe we implemented it in the Great Plains or much of the Eastern US, kind of with that idea in mind. You know, coming from Iowa, the attitude of prescribed fires in tallgrass prairie was, if it'll carry a fire, you should burn it, even if you can burn it year after year. So we're very aware of that and try to make sure that we're capturing those repeat burns.
And we're seeing down here in Florida, in some of those repeat areas, we're capturing it in places that had a one-year rotation, we're capturing that. So I think your filter works.
Good. Thanks, Casey.
There's a question that came in from Talat, and he's asking if there were any noticeable differences in the accuracy by geographic region.
Yeah, that might be a good question for Melanie to chime in. Like with version 2, the accuracy metrics are fairly hot off the press, and we haven't done a whole lot of, I haven't looked at them a whole lot by different regions, but in the papers for the burned area version 1 products, we tried to break things up by different regions and different cover types. And our plan is to do that in the publication that we're working on presenting the version 2 data. But Melanie, maybe if you're still on the phone, if you want to chime in there, that'd be really great.
I don't know if we have her audio. Let's see. She's called in. I may be able to give her microphone rights.
Yeah, definitely the last 2 papers that Casey has listed here in her slide will present some of those results though.
Yep, I can't pull her in right now, so we can look for those results.
Okay.
We had a question that came in, a couple folks asking about comparing this product, excuse me, to the Ravage maps.
Yeah, so let me think here. The Ravage maps are sort of these rapid assessments that you do with the most recent Landsat imagery after a fire. Is that correct? I'm not sure I can do that comparison because I'm not fully familiar with their methods. I'm probably more familiar with what monitoring trends and burn severity does with their initial assessments, which I think might be similar. our methods are designed to be as hands-off as we possibly can. Like we spend a lot of time kind of training and tuning the initial model, and then we just apply it to every image in the archive and just let the computers rip. And so, and there's advantages and disadvantages to that. The advantage is that we've pretty much looked at every pixel that we possibly can. The disadvantage is that we don't have a whole lot of manual interpretation of what's actually happening on the ground, like I think Ravage does, or like MTBS does. And so, yeah, so I guess our advantage is just the completeness. And I think things like Ravage and MTBS, the advantage is the manual interpretation, but they're only done for specific fires as far as I know.
And I'd add to that, Todd, that the MTBS and the Ravage actually show kind of, or end up classifying into severities, and we just do burned or not burned with the burned area product, which is somewhat different. Yep,
excellent point.
That gets to a question that I think I had on my list to ask y'all was about severity. Do you see any future opportunities to investigate severity with this product?
Yeah, I think that would be a natural add-on. The challenge there is training an additional model to classify our burn pixels into different severity classes. And Josh Bricott, who I think was on the line, has probably the most experience doing this, and that's who we'd look to kind of use some of his more recent work to actually classify severity. But we haven't yet. But if it's something that people are interested in and really want to see, it's great to get that feedback directly from people, because then that's something that we can promote to our program coordinators and headquarters and make sure that kind of work gets funded.
I ask that because I know there's been quite a bit of interest in the Southeast, in particular in terms of coming up with tools to map the amount of fire that we see on the landscape. And a lot of that interest goes back to estimates of emissions and tying that to state air quality.
Yeah.
And so having a sense of not just the area burned, but how much of it burned and to what extent could then be tied to fuel loads and then emission factors to then scale up to regional emissions. But I guess one way you might be able to address that, I suppose, is if you knew time since the last fire, you could sort of estimate potential emissions based on the potential fuel loads that you had in there.
Yeah, you could certainly do something like that. You could also look at, in our annual mosaics, things like differences in the burn probability. Usually higher severity burns have a higher burn probability, and they also persist longer through time. And Melanie's done some work kind of looking at how persistent is that burn classification and how does it relate to severity as well. So we've got some ideas on how we could do that, but haven't had a full-blown effort to actually implement it for our data products yet.
And here's an interesting question that came in from Andy. He is asking about omission and commission errors as a function of fire size. And he says, presumably large fires are easier to detect than small ones. And how small of a fire can you reasonably expect to detect with decent accuracy?
Yeah, that's a great question. Large fires are easier to detect, and we can detect them with greater confidence. Small fires get to be challenging in part because with Landsat imagery, the smaller the fire gets, the harder it gets to do any sort of visual interpretation. With version 1, we did a lot of work to compare our results with the raw Landsat imagery, but also with other spatial fire data sets like the GeoMac data, especially because they had perimeters for fairly small fires. And sometimes it was great, like we'd have a 5-acre fire and we nailed it. And other times we'd have the small burn patch in our results and we couldn't really tell what it was. So with version 1, we kind of decided that 10-acre size was probably reasonable. In version 2, we've actually gone down to 5 acres in size. We've gone from there. So
we had along those lines, we had a question come in for Casey from Amy. And Amy asked, did your team consider fires smaller than 10 acres in size? And if so, did you handle them differently in your data set than fires over 10 acres?
No, we basically followed the USGS stuff. We think that we might be able to get down to 2.5 acres, just looking at a pixel by pixel basis. But we're going with what the USGS has right now. So we can filter out things smaller than the 5 acres. We'll leave things larger than 5 acres in there. And that's part of that revalidation with that, specific, all that data call that we had with all those data sets, and with this version 2 burned area product, we can start looking at some of that.
We had a question that also came in regarding funding to periodically update that version 2 algorithm in the future. Could y'all both talk about where are your projects going, and what does it look like for the future of both of these efforts, the national product and the regional efforts?
Sure, yeah. Casey, do you want to start on that one, or do you want me to take it?
Sure, I'll start regional. I know in the Southeast there's been a huge amount of interest in this, considering the amount of burning that's done in the Southeast. So there's interest in furthering this effort in terms of validation, updates, going back in time, all that stuff. As far as funding, I'm not 100% aware of all different sources. I do most of the analysis and let my supervisor deal with that, but there's definite interest in carrying this forward. Some of the talks, this was through the PFLCC and the FWCC for their purposes. So once we turn this over to them as a final deliverable, then I think we can start figuring out if and how some of this stuff can be hosted locally or regionally. And then I'll let Todd go from there, bigger picture.
Yeah, so from USGS's perspective, I think the plan right now is to continue routine production with version 2, and hopefully getting that to be fairly on demand, or at a minimum, just processing things a year at a time. We have all sorts of ideas, of course, about how to improve the algorithm or how to apply it in other parts of the world. We had a student who did some work applying our algorithm in Uganda and found pretty good results. Funding at USGS right now, it's quite variable year to year, and our team here in Denver, we've actually kind of moved on to some other things, looking more at fire emissions and fire risk and disturbance impacts on carbon cycling across the country. And our involvement with the burned area work is right now kind of wrapping up manuscripts and getting the final national mosaics out there. But my hope is that after a couple of years of having those data out there and getting feedback from end users, that we can then go back to headquarters and say, like, hey, it's time for an update. These are sort of our top 5 priorities that we want to address, and go from there.
Based on the interest we've had and the number of questions that have come in, it sounds like a lot of folks are curious to see more, maybe to play with some of this data on their own. One question for you, Casey, is do you know if there will be a way to share the results of this project publicly in the future?
Yeah, that's a great question. Like I said, we were contracted to do this work, and so I know Fish and Wildlife here in the state is going to be taking over that data set. That being said, Tall Timbers is interested in providing this as some sort of service as well, whether that's a web service or tying it into some bigger overall project. I'm not sure what that looks like, but we can work with people as soon as we hand this off. I think we're able to work with people on other ways of getting information out there. So we're happy to work with people on that.
All right, so it sounds like if they're interested in having access to this in the future, depending on how it ends up through FWC, if they reach out to you, you may be able to put them in contact with the folks over at FWC as things move forward.
Correct.
All right, great. Well, we have contact information, email addresses for both Todd and Casey on the screen now. So if you have additional questions about the projects that they presented on today, you can reach out to them directly. One last question I see that came in from David, and I think it's quite interesting because I've seen some recent examples where the Google Earth Engine has been used to handle massive amounts of data. Do you know, Todd, if there's any possibility of being able to share that, the burned area products, with Google for pulling it into the Google Earth Engine?
Yeah, we'd be absolutely happy to have our products in Google Earth Engine. We've talked with a few people on their team in the past, and they said it's basically, it depends on how many people request to have that data set in their, in the data sets that they serve up. So if that's something you want to see, you basically have to contact Google to get enough interest.
All right, well, we'll tell your friends and shoot them some emails, and maybe it'll show up in there, and that'd be pretty cool. All right, well, it looks like we have run up to the end of our time today, and the questions have slowed down. So again, if you had any additional questions or comments for our speakers, email addresses are there on the screen. Thank you everyone who joined us today. Thank you especially Todd and Casey. I appreciate all your effort and your presentations. And have a good afternoon, everybody.
You're welcome. Thank you for all the work organizing, David.
Yeah, thanks everybody.